Hello everyone, this is the Prophet Michael David, aka Aries, and today we're going to go over the Collatz game, Mersenne primes, and perfect numbers. Yes, they are all related. And this is going to be the first video in at least 2 videos, maybe more. That is the last YouTube video that Veritasium made on perfect numbers, and it was incredible. But there was one specific part which got me thinking about this problem instantly. So that's Leonard Euler, the greatest mathematician to ever walk the earth, saying that. So when Leonard speak, that's basically he's saying this is impossible. For if it were possible, I would have solved it already. And so I saw that and I thought, I got to take a shot at this and figure it out. And I did. And here's my conjecture. Okay, so I made this sound kind of as mathy as possible, like mathematicians would, and I'll read it to you right now. Now, I'm not going to describe the whole thing, but all perfect numbers must fall on modulus lines in the form of A mod B. We've talked about mod lines before. Where, and these are the 3 conditions, A is the final digital root that square primes can be. We've talked about digital roots before, but look it up if you need to. So all primes squared, like 5 squared is 25, 7 squared is 49. Okay, second constraint is B is a final digital root that primes cannot be. So these are digital roots that primes are forbidden to be, regular primes, not prime squares. And number 3, A plus B must equal 10. Okay, here's how I'm going to do this. I will fully explain that equation and constraints and how I came to them, and that will prove that there are no odd perfect numbers, as well as you can prove anything about perfect numbers. But from here, the rest of this video is going to go back into Collatz, but then that's going to bleed into Mersenne primes, and then, of course, Mersenne primes will bleed into perfect numbers. So here we go. So that is the most famous geometric sequence in history, and that is what this is all about. Remember what I told you about in the Collatz game, that it's all about 3x plus 1, and then you divide by 2 a certain number of times, depending on how many 2's you have in that number. And that's the probabilities on those are exactly the same as that geometric sequence. 1/2 the time, you will 3x plus 1 divide by only 2. 1/4 of the time, you will 3x plus 1 and then divide by 2 and then divide by 2 again, aka divide by 4. 1/8 of the time, you will 3x plus 1 and then divide by 2 3 times, which is 8. And that's why that geometric sequence shows that, yes, that all the probabilities do end up to equal 1, 100%. So I did it another way in another video, but I was working with binary at the time because I've done a binary Collatz video as well, and I knew the zeros on the end of the binary were just the number of 2's. And so I just wrote down all the 3x plus 1, aka 4 mod 6 lines, 4 mod 6 numbers, and then turned them into binary, and then made a list of the numbers of 2's that were in those numbers. And then I graphed it to see how it looked on which numbers had which numbers of 2's, and it looked exactly like the other one that I had made the exact other way. But that's when I had an epiphany. So I knew, as I've stated before, that the only time you get gains in the Collatz game is when you 3x plus 1 up and only divide by 2 once. If you put any number into x, the number will always end higher if you 3x plus 1 and only divide by 2 once. Now, if you 3x plus 1 and divide by 2 twice, aka divide by 4, those numbers will always go down, except if x is 1. That's the only exception, and that's why it gets caught in that loop at the end of every Collatz game. And the ones other than that, 3x plus 1 divide by 8, numbers will always go down. 3x plus 1 divided by 16, numbers will always go down. 3x plus 1 divided by 32, numbers will always go down in utero. And that's when I had my epiphany. I thought, well, if you only get gains in the Collatz game when you 3x plus 1 and only divide by 2, and that statistically happens half the time, then statistically a quarter of the time, 1/4 of the time, you will get a number that 3x plus 1 divide by 2 once, and then it's odd again. So you 3x plus 1, and then you divide it again 2 only once. But then I thought, well, then 1/8 of the time, that series will happen 3 times. You never worry about the 3x plus 1 divide by 4s because you never ever get those numbers. You'll get a consistent chain of 3x plus 1 only divided by 2 once, and then that chain of 3x plus 1s divided by 2 would always go up and go to infinity. I mean, doesn't there have to be a chain like that statistically if all probabilities add up to 1? And then I thought about it, and I came up with this graph or screenshot. So that's exactly what I did. I took all the odd numbers that you can put into 3x plus 1 that would 3x plus 1 up to a number that would only divide by 2 once before it became odd again. And those are all the pink numbers on the left side. Those are the first generations of my 3x plus 1 divided by 2 numbers. So then I thought, just like my probability thought experiment, that'll happen again, but only half of the numbers in the second generation will be pink. And I was correct because only half of them can 3x plus 1 divide by 2 and then 3x plus 1 divide by 2. That'll happen a quarter of the time. And as you can see, I did that for subsequent generations because I knew it would just be the numbers in the second generation would also be in the first generation. And so it ended up, I went out to 6 generations, and you can see it forms chains. And as you can see, as the numbers get bigger, the chains get longer and longer, but the chains always end. And there's a mathematical relationship between the end of the chain and the end of the longer chain below it. And that's always, you take the end of the first chain and that's x and 3x plus 2, and that'll be the end of the other chain. So as you can see, the chains get longer and longer as the numbers go up to infinity, but the chains always end only to have one below it that ends with the number 3x plus 2 larger than the end of the other chain. So they can never go to infinity. So there's my Collatz algorithm again that I like to throw in all my Collatz videos that shows very succinctly why the Collatz game can't get to any loop except the 4-2-1 loop, as I've described before. It also explains the infinity thing, although you have to think about it more logically, but it is a very good visual proof. But my argument with the chains of 3x plus 1 divided by 2 only also confirms that the Collatz game can't go up to infinity. While yes, the chains do get very, very long, there's always going to be a longer chain than that one. And the other thing is, but to get to those longer chains, eventually your starting number gets almost infinitely big, or at least undefinable. So that doesn't help you find a Collatz game because those numbers are going to be like, for us, pretty close to infinity, way over the 2 to 68 that they've checked. All right, so that's pretty much the end of my proof on Collatz. I really can't dumb it down any more than that. Not that I'm calling you guys dumb, just any mathematicians that don't understand it dumb. But before I close down here, I'm going to bring up some of my inspiration and sources that I used for my last video, including that screenshot that was the thumbnail. I like to cite my sources better than I did. I only did it because I was running out of time. So here we go. All right, so that thumbnail, that cool looking Collatz thing was from that article from that website that I just posted there, where this gentleman did a very good analysis on the Collatz conjecture. But I'd like to use it, it was both an inspiration, but I'd like to use it to teach you guys that what I've taught you, you can explain a lot of his problems or a lot of his questions. What he calls hard numbers, I call magic numbers. So in his results, he had two huge questions. Was like, number one, why do so many games end when it goes down and hits 5, as opposed to the other magic numbers, what he calls hard numbers and everything? And that's because, like we talked about earlier, only if it 3x plus 1 goes down 2, it's trying to go up to infinity. If it 3x plus 1 goes down 4, it's trying to go down to 1, which all college games get caught in. 3x plus 1 down 8, it's trying to go down to a fraction in between 0 and 1, which is 1/5, because if you set 3x plus 1 equal to 8, 5x equals 1, x equals 1/5. And then 16 will be 1/13. They all become fraction. Most of them are fractions of primes. But everything is trying to fight down to 0. And so that's why a lot of games end very quickly. They get down into an area, and 5 has the most progeny out of all of the magic numbers. And so it's much more likely that it's going to hit a progeny of 5, slide all the way down to 5, and then go up to 16 and end the game. And that's why there's a huge asymmetry. And yes, most games are going to end at 5. Or most games are going to go down to 5 before it ends. And then the second big question was why almost no games end with 21. And as I've described before, that's because 21 is located on the 3 mod 6 line and therefore has no progeny on the 4 mod 6 line, like the 1 mod 6 line and the 5 mod 6 line do. All of the 3 mod 6 lines progeny are on the 6 mod 6 line. So the only way that 21 is going to get hit is if you pick 21 off the bat, you pick 42, you pick 84, you pick 168. That's why so few games have 21. Although, as I've said before, that a lot of people say, I've seen a lot of Collatz games with 21, is because everybody picks 42 because of hitchhikers. And lastly, that's a pie graph chart that he had that's also very good, where he asks the same question, and it again supports what I just told you. Fun fact, so it explains why 5 dominates and why 21 has almost none, but that other one at the top, 1365, that's the next magic number, aka hard number, that is located on the 3 mod 6 line. So that's why there's none of those. Or if there are, there's like one of them, because you're only going to get, that's only going to be in your Collatz game if you pick 1365, or if you pick a number that's 1365 times 2 times 4 times 6 times 8, because then it'll be located on the 6 mod 6 line and decay down into that number. All right, I'm going to sign off now. A little bit over 12 minutes, but not too bad. You might be saying at this point that, all right, you talked about a lot about Collatz again, but you didn't talk about Mersenne primes or perfect numbers at all. But they were in there. It's they're kind of hidden, Scooby-Doo mystery. But I assure you that you did see and hear some about them. You just didn't know unless you look closely, which I'll fully explain in the next video. And then if I have to have a third add-on video, then I'll do that as well. So as always, rule number 1, do not touch other people without their consent, aka do not hurt each other. And rule number 2, it's all about honesty. Lies are ticked down, aka try not to lie. All right, I'll talk to you guys later.